Well, good evening and welcome to Tellus. It's great to see such a wonderful crowd here. I'm Dave Dundee. I'm Director of Education, and we have an exciting evening for you. By the way, after the lecture at 8 o'clock, there is a planetarium show called Birth of the Earth. It's a show that Tellus was involved in developing the script for, and it has some excellent computer animations of how the solar system formed. If you're interested in extraterrestrial things, our observatory is open until 10 o'clock. The museum is open till 9. And we've got a lot of things coming up here at Tellus. Next week, we have scheduled a lunar eclipse, and it's not quite total. 97% of the moon will be covered. It happens in the wee hours of Friday morning, starts at around 2 a.m. and ends shortly before 6, so you can see the whole event and then drive off to work right after that. And on Wednesday, the midday, if you don't want to go for crazy hours, there is a talk given by me here for our Lunch and Learn series about the lunar eclipse. And then December 3rd, we have Alan Kressler here. He is a world-famous cave photographer. And if you're into caves, that's really cool stuff. And that will be the opening night of our new cave exhibit, which is under construction at this very moment. We're building a cave in our temporary exhibit area. It's really going to be very, very cool. And for that weekend only, we will have a portable cave being brought to Tellus. Didn't know they had made those, but they do. And you'll be able to climb through or crawl through or walk through this portable cave exhibit. And then the following weekend, we will have a special weekend. It's our annual PJ Day, where Santa will be here on that Saturday. But we'll also be filling both Saturday and Sunday the Great Hall and the banquet room full of running model trains. So if you're into trains, we're going to have trains everywhere, from G-gauge, the big ones, to the small ones, N-gauge. We even have a Lego train club coming with a moonscape of trains on the moon. And so it's going to be a very, very cool weekend. So please come back for that. You've heard of Festival of Trees. We have Festival of Trains. So anyway, I want to introduce now our Executive Director, Jose Santamaria, who's going to introduce our speaker tonight.
Thank you so much, David. Well, you sure know how to get their attention. Eclipse, caves, model trains, whoa, yeah. I heard that size. Well, Tamie, we're finally doing this. I think we started talking about doing this 4 years ago when Dr. Tamie Jovanelly first told me about her research going towards writing her book. And we had this event scheduled 2 years ago, and then due to circumstances beyond our control, as in delay in publishing, not her fault, we rescheduled it to April of last year. So what happened last year? Well, we had to reschedule again to a point that we felt really comfortable we could pull this off. So once again, thank you all for being here. I love having the big Berry presence here, and thank you so much for Berry College for helping sponsor this and helping making these books available to give away to some very happy people. Tamie introduced herself via email, a very enthusiastic email, by the way, about 15 years ago when she first came to Berry. And of course, once I met her in person, enthusiasm is the word. She's associate professor of geology at Berry College in Rome, and very highly rated by her students. And in fact, we have had 7 interns here recommended by her. At least one who's in here. Her bachelor's is from the University of Michigan, a master's from the University of Nebraska, and a PhD from Kent State University. Among her many accomplishments are her research has been funded by Fulbright, National Science Foundation, and National Geographic research grants, among many others. She first explored Iceland in 2006. She's taken at least 6 geology trips to Iceland with her students in the summer. And along with her husband, Joe Cook, she is now co-founder of Iceland Geology Tour. So if you want to go to Iceland, you know who to call. So it really grants me great pleasure to finally welcome to tell us for this lecture, Dr. Tamie Jovanelly.
Thank you. Finally, huh? So, Jose, I don't know if you realize it, but we might be making history here, because I don't know it for a fact, but I think I'm the only geologist that wears a sequin dress. I don't know it for a fact, I just know. So thank you so much for the warm welcome. I'm really excited to be here tonight. It's been a journey for sure to get us here. Again, my name is Dr. Tamie Jovanelly, and I'm an associate professor at Berry College, and I'm also the author of an advanced geological studies book about Iceland. As you become familiar, the book is organized into 3 major parts focusing on tectonics, volcanics, and glacial features, and that's very much how this lecture will be organized for you tonight. But before I get started, most people are interested as to how I ended up in Iceland in the first place. And my first trip to Iceland was in 2006, really when the island was off of the radar for most tourists. I convinced my big brother Jim to tag along with me, and in the course of about 11 days, we circled the island using what's called the Ring Road or the Golden Circle Road. And in 2006, this is truly before like GPS technology, so we had a series of these paper road maps, and we were trying to navigate by the sun, but we quickly realized that there's 22 hours of daylight in July, so that wasn't going to work out. And there weren't many road signs, so we found ourselves perpetually lost, but we were perpetually lost in a beautiful and pristine landscape that would bring me back nearly every single year thereafter. In 2014, I acquired a wonderful husband who has an amazing sense of direction, and we began to explore even the most remote places of the interior through backpacking and hiking. And for me as a geologist, this was really a game changer, because for the first time it allowed me to synthesize the entirety of the island instead of thinking about them in specific different categories. I initially went to Iceland in 2006 to set up a study abroad program for Berry College geology undergraduate students. And I have some students that have come along with me here in the audience today, and they're also in these pictures. So fond memories that we have on some of our study abroad trips. So I went there initially in 2006, and I was interested in studying, in organizing a field studies course. And I looked down in 2006 and recognized that there wasn't a book. So I started to collect my own scientific literature on tectonics, volcanics, and glaciers. And in doing this for more than a decade, I finally looked down in 2017 and realized I probably had enough information to write a book. So I then, of course, looked to some of my colleagues. I have a colleague here, Mike Morgan, and I went to his office and I said, what do you think about me writing a book? And he's like, what do you got to lose? And then my hero and champion, my former dean, Bruce Kahn, told me that you're not an expert before you write the book, you're an expert after you write the book. So that gave me the confidence to dive into this literature and this place that I love so very much, and I've been excited in working on the manuscript. I love the process of writing the book. I love the solitude of it, and I loved all the light bulb moments that went on. So I'm excited to write my second book. My husband is less excited for me to write my second book, but it looks like I'm going to be investigating the geology of Europe next. So there's one more thing that you need to know before we move forward, and that is... And that is, I don't speak Icelandic. Thank you, Google. As you heard, it's a pretty complicated Nordic language, and although I practice with really good intention, I never quite nail it. So I apologize in advance for my mispronunciations. And additionally, because this is a talk on geology, there'll be some acronyms that you see on my slides. That includes millions of years old, millions of years ago, modern time will be referred to as the Common Era, and historic time will be referred to as before Common Era. And on my slides and figures, you'll see this yellow star, and that's going to represent a hot spot or a mantle plume, and we're going to see how that's a driver of the geology we see on the island of Iceland. So I want you to sit back and relax, let me do the work, and I'm going to talk to you about my top 10 geologic wonders of this amazing place. And to do that, we are going to start by thinking in terms of plate tectonics. So you may be aware that the Earth is not a static system. It is instead a dynamic system. And when we think of the organization of that dynamic system, we are looking at 7 major tectonic plates and 12 minor plate tectonic plates. I'll call your attention to this modern plate tectonic diagram. And we can locate ourselves on the North American plate, highlighted in purple. We can see the eastern seaboard, Florida, and the great state of Georgia. And adjacent to the North American plate is the orange Eurasian plate. And what separates the North American plate from the Eurasian plate is a divergent plate boundary. And a divergent plate boundary is when you have 2 plates that are moving or spreading apart from one another. And conveniently located on top of this divergent plate boundary is the island of Iceland. Iceland is sitting at approximately 66 degrees north. It is approximately 38 miles south of the Arctic Circle, and it's bordered by the Arctic Ocean to the north and the cold, dense, and saline bottom waters of the Atlantic Ocean. I have some students here who've done a polar plunge in the Atlantic Ocean during the study abroad trip, so they can testify to how cold it is. So Iceland is sitting at about approximately 66 degrees north. It's up at the top of the globe, and what's interesting is that the geological history of Iceland is pretty unique, especially if we consider the age of the Earth to be 4.6 billion years old. The story of Iceland only begins at the last Pangea cycle, approximately 50 million years ago. And it is at approximately 50 million years ago that we see the very first organization of what we call a hotspot or a mantle plume. Those terms are synonymous. And a mantle plume is when you have a body of magma that's upwelling from the subsurface, and it's moving closer and closer upwards towards the crust. And as it does, it's giving off heat. And as it does, it's giving off heat. So we see the very first signatures of those at 50 million years. And what I need you to remember is that the hotspot itself is stationary. Instead, what's happening is that the plates are moving over top of that hotspot. So when we look at the diagram on the screen, we can locate the presence of the hotspot approximately 50 million years ago, and we can follow its trail all the way up to modern day, with modern day being represented by 0 on this diagram. So there's currently a mantle plume that's underneath Iceland. It's approximately 200 miles in diameter, and that's pretty significant if we consider the overall size of the island of Iceland. When we look at this diagram too, highlighted in red is the presence of the modern day divergent plate boundary. So as the story goes, at approximately 33 million years ago, that mantle plume was close enough to the oceanic seafloor to begin to breach. And as it breached, it brought layers upon layers of basaltic magma to create the island of Iceland. Basalt is a type of igneous rock. So when we consider the Icelandic basaltic plateau at modern day, we only see about 30% of the island. The remaining 70% is submerged underwater. And when we begin to consider the stratigraphy of the rocks, or the ages of the rocks, we can orientate ourselves to the yellow star, which represents the hotspot. The divergent plate boundary is highlighted in pink on this diagram. And we can look adjacent to that pink divergent plate boundary to notice two parallel red bands. And those two parallel red bands represent rocks that are 2 million years old. And that should start to make sense, right? So when you have divergence, you have the spreading or splitting of this island. It's allowing for a conduit of magma to come more easily up to the Earth's surface and begin to solidify. So the youngest rocks are going to be closest to the hot spot. And by the time we make our way to the east and to the west, to these yellow parallel bands, that's going to represent rocks that's approximately 10 million years old. So if you have the great adventure to go to a city called Eglasador in the far east, or to the western fjords, you're going to see the oldest rocks on the island, but those are only 13 million years old. So in terms of geologic time, Iceland has barely had a birthday. Thank you. So let's consider that mantle plume a little bit more. The mantle plume is a system in and of itself. So again, you're considering that hot magma that's upwelling, but as it gets closer and closer to the surface, it's going to eventually cool and condense. So you end up with these density-driven systems within the magma plume. And those density-driven systems are going to be called convection cells. And those convection cells have circulatory motion. So it is the circulatory motion that we find in the hotspot that's acting as a driver for the plate tectonics that we see on the island of Iceland at modern day. So when we consider the rate of divergence, what we say is that the plates are moving or spreading apart at 1 inch per year or 13 miles per million years. What? Yes. 1 inch per year or 13 miles per million years. So if you're interested in buying property in Iceland, I encourage you to buy it along the divergent plate boundary because your property size will only be getting bigger. You might have to deal with volcanoes and earthquakes, but there's insurance for that. When you have the great adventure to go to Iceland, undoubtedly you're going to make it to the capital city that's called Reykjavik. And even if you're there for a layover, even if you're there for a half day or a full day, I hope that you hop on a bus and take it 2 hours to the east to a location that's called Thingvellir. And Thingvellir is highlighted with this yellow star. So Thingvellir is one of the only national parks in Iceland. Thingvellir is home to the Icelandic parliament that initiated in 874 CE. And the question might be, why did the Vikings choose Thingvellir? But when we look at the picture, we can see that there's upper elevation and there's even a lake, which is really unusual for the island of Iceland. And this is called Lake Thingvellir. So it's a beautiful place, and it's probably why one of the Vikings decided to settle there. And you'll also notice that it's some distance away from the coast, so the climate is a little bit gentler the further you go inland. But for a geologist, Thingvellir is even more exciting because it is one of the only places in the world where you can see a divergent plate boundary exposed on the Earth's surface. So you can literally be in the park and stand on top of the Eurasian plate. And remember that in the first diagram, the Eurasian plate was in orange. And you can look across 13 miles to the North American plate. So you're standing on the Eurasian plate, you're looking 13 miles across Lake Thingvellir to the North American plate. And this should start to make sense, right? Because what we said was the plates are moving or spreading at 1 inch per year, or 13 miles per million years. So we can even add an age date to the spreading that we see at Thingvellir. This geological feature is called a horst and a graben. So the upper elevations of the Eurasian plate and North American plate are called the horst. And as you continue to have spreading, what ends up forming is a graben. A graben is the basin that's holding Lake Thingvellir. So as you continue to have tensional pulling apart of these plates, that graben continues to subside. So Lake Thingvellir is getting deeper and deeper with geologic time. If you're in the park, you can choose to go scuba diving. I met a fellow here, Bart, and he snorkeled along the mid-Atlantic ridge here on Iceland. I'm not going to do that. It's way too cold for me. But I'm glad that he had the opportunity to do that, and he said it was quite beautiful. But one of the things that I do love to do, and I pull Joey along with me on these adventures, is I love to go hiking. And in Thingvellir National Park, there's about 10 miles of hiking trails that you can explore. And one of our very favorites is looking at Almaja, because it gives you true and active examples of the plate tectonics that are happening. Because as you're meandering through these paths, you're seeing the blocks of basalt slumping and slumping as the plates continue to be pulled and pulled apart. So it gives you a very dynamic picture of the active plate tectonics and rifting that's always occurring. So here's your fun fact that you're going to take with you, because you're going to see it on trivia. And your fun fact is, Iceland, that is about the size of Virginia, has 33 active volcanoes. What? I'm going to repeat that. Iceland, that's about the size of Virginia, has 33 active volcanoes. So pretty much anywhere you look in the landscape, you're going to either see an example of an active volcano, a dormant volcano, or some type of volcanic feature. When we look at this map, we can orientate ourselves again with this yellow hotspot. And the volcanoes, the 33 active volcanoes, are located on this diagram, and they're numbered. So I want you to take a look at this diagram, and hopefully what's happening is that a pattern begins to emerge. So I'm asking you to look at the position of where these active volcanoes are, and you should say, Dr. Joe, those volcanoes are outlining the divergent plate boundary. They're outlining the divergent plate boundary. And that makes sense because we said when you have rifting, you have magma that's more easily accessible to the Earth's surface. So these 33 active volcanoes are outlining the present day divergent plate boundary. The black dots represents those volcanoes that are now dormant or extinct. When we talk about volcanoes in Iceland, we classify them into three major categories. We talk about the northern volcanic zone, the western volcanic zone, and the eastern volcanic zone. And the eastern volcanic zone is along the southern portion of the island, and it borders the Atlantic Ocean. So when you talk to a geologist or a volcanologist about the biggest and baddest volcanoes on Iceland, but arguably in the world, we are going to locate them in the eastern volcanic zone. I'm going to talk to you about some of my favorite volcanoes. That includes number 13, and I want you to notice that it is not on the mainland. It is in the Atlantic Ocean. We're going to take a look at 14, 15, and 16, so let's cluster here. But before we do that, I'm going to take our attention to number 32, which is the volcano that's called Bardabunga. And Bardabunga had what we call a fissure eruption in 2014. So Bardabunga is a classic volcano that you can imagine in your mind. It has steep flanking sides, and it has a central magma chamber. But what I want you to recognize is that as that magma is working slowly up to the Earth's surface, it also spreads away from the central vent, and it spreads laterally. So as that magma is coming to the Earth's surface, we have to accommodate for that new mass. And we do this by creating fractures or fissures like you're seeing here. So those fractures and fissures are allowing a conduit for that magma to more easily come up to the Earth's surface. And I show you this fissure eruption because what I told you was that at approximately 33 million years ago, the Icelandic basalt plateau formed, and it was likely formed in a situation that was very similar to this, where you had magma upwelling through the oceanic crust and being deposited. So as you can tell, fissure eruptions drastically change the landscape. There have been two major fissure eruptions on Iceland in modern time. So there was a fissure eruption in Mývatn. Mývatn is a city in the north from 1724 to 1729. And then, even more recently, there was a fissure eruption at a volcano called Katla. Katla is in the eastern volcanic zone. and that eruption occurred from 1975 to 1984. So geologists have a really good understanding of how these fissure eruptions translate and change the modern day landscape. If we consider geologic time, we can think of a time that was called the Permian. And the Permian period, 248 million years ago, ended in a mass extinction, probably tied to a fissure eruption that occurred in Siberia, where the fissure opened and over the course of 1 million years brought about 2 miles thick of basaltic lava to the surface over the areal extent of the United States. So a massive fissure eruption in the Permian led to a mass extinction 248 million years ago. So in addition to the heat that these systems bring up, we also see greenhouse gases, water vapor, carbon monoxide, and carbon dioxide. So they can be quite devastating. Now, I also want to talk about some of my favorite geological features. So one of the reasons why volcanologists and geologists go to Iceland is because the island has 33 active volcanoes, and as a result, you can see just about every volcanic feature on the planet in one location. These are 3 of my favorites. The first one is called a rootless cone. And a rootless cone is also sometimes termed a pseudo-crater. And although this kind of looks like a volcano, we can see the caldera, instead of these forming from magma coming up from the subsurface, what happens instead is that lava is flowing on top of the Earth's surface, and it comes into contact with water. And that water might be steam, it might be a swamp, it might be a bog, it might be a body of ice. But as that lava comes into contact with water, you get a one-time steam eruption that drastically scars the surface and leaves behind a crater. So this crater is in a location called Mývatn in the north of Iceland. We can see the road, and then up here there's tiny, tiny people to give you a perspective of shape. So after the one-time steam eruption, these will go completely dormant, but they drastically change the landscape. And oftentimes when we talk about rootless cones, we talk about them in terms of a rootless cone complex. So in Mývatn, there's 21 of these different craters. And it's really neat to look at these aerially because you can tell the direction of which that lava was flowing on the Earth's surface. These range in size. There's another location that's called Rúðhólur, and Rúðhólur is in the south of Iceland, and there were 51 different craters. So when you're there and you're walking through these crater fields, it kind of gives you the feeling like you're on the moon. The next is called columnar basalt, and columnar basalt is truly a physics phenomenon. In this situation, the magma is coming up from the subsurface, but this time it's trapped by ice. And the presence of that ice quickens the rate at which that basaltic magma cools, and so you get contraction. And it's solidifying from the top down, so you end up with these long and beautiful columns that become evidence of the geologic record. Similar to rootless cones, these range in size and they range in height. This example is in a location in the south called Vik. Vik is also called the Black Beach. And probably most important to my research as a climate scientist is I'm interested in looking for a structure that's called a pillow basalt. And you might be familiar with pillow basalt if you've been watching the Hawaiian Islands eruptions in 2018, 2019, because we can see these form at modern day. How this works is that you have lava flowing down the flank of a volcano, and this time that lava meets the ocean. And instead of having contraction, like we did with the columnar basalt, in this situation we have expansion or inflation. So you end up with these beautiful, beautiful pillow structures. So if you're driving around the perimeter of the island and you notice a pillow basalt, then you have an indicator of where the ancient or paleo sea level used to be. And of course, you have to work in uplift and subsidence and erosion, but it gives a climate scientist an understanding of where to start, of where the ancient sea level might have been. And then, of course, we can go ahead and geologically date these to get an even clearer understanding. The great thing about being a geologist in Iceland is that we don't have it all figured out yet. So there's still some remaining questions that we like to debate. And one of the big questions that we like to debate is why on the island of Iceland do we see the presence of both explosive and non-explosive volcanism? So an explosive eruption is your classic video that they show on CNN where you see Mount Pinatubo erupting and you see that huge white ash cloud billowing up into the atmosphere. That's an example of an explosive eruption. When we define an explosive eruption in geology, we look at the mineralogy of its magma, and we define the mineralogy of that magma to be felsic. And what that term means is that you have a high amount of silica embedded in that magma. So silica is SiO2 elements, and they're bonded together. And as they're bonded together, they form a really strong covalent bond. So when we talk about felsic magma, we say that it has a high viscosity or a high resistance to flow. So you're imagining that magma trying to go up the throat of that volcano slowly, slowly, and as it does, it's trapping and trapping volcanic gases. So eventually, when you have an eruption, you have a huge ash cloud that usually forms pumice and is often light in color. So we see explosive volcanism on Iceland, but we also see non-explosive volcanism. And non-explosive volcanism is your classic Hawaiian island example. So you've seen pictures of people and they're taking their selfie, and the volcano of the Hawaiian Islands is erupting behind them, and they really don't care because they just want to get a good picture, right? You've seen that? Well, they're not in any grave danger because it's considered to be a non-explosive eruption. The magma has a mineralogy that we call mafic. So it has a low amount of silica, it has a low viscosity, and a low resistance to flow. So the silica is often replaced by magnesium and iron, so it gives it that dark color. So the question remains, why on Iceland do we have explosive and non-explosive volcanism? Why do we have a difference in these magma chambers? When we talked about Iceland, what I said is that there's a hot spot that's present. It's 200 miles in diameter that's underneath that southeastern corner. Also, the Hawaiian Islands have a hot spot. That's where the generation for that type of event happens. So theoretically, Iceland should only have mafic magma. It should only have non-explosive volcanism. So the theory is, there's two different camps of thought, is that the felsic magma is a result of slow crystallization processes. So the idea that the heavy metals are precipitating out by the time the magma gets closer and closer to the surface. The other camp of thought is, remember I showed you the origin of that hot spot 50 million years ago, and it was under Greenland. And so Greenland is continental crust, has a high felsic contribution. So perhaps that magma plume picked up some of that felsic material and has carried it with it for the past 50 million years. So it's still under debate, but the great thing is that because we have the presence of explosive eruptions, we have some pretty intense geology to start to talk about that has led to some pretty impressive eruptions over geologic time. When we study volcanoes, we use a science that's called Tephra Chronology. Tephra is another word for volcanic ash. So what goes up must come down. And so those layers of volcanic ash will then eventually get preserved in the stratigraphy or the geologic record. So we can take a soil core or we can take an ice core, and we can have an understanding of how many volcanic events have happened and their intensity. Each volcanic event has a different mineralogy, and so it's like it has a different fingerprint. So in knowing that, we can work backwards to figure out the source of where these volcanic events have happened. And for one event we can use as an example is Askja that happened in 1856. It is modeled that when Askja erupted, it had a felsic eruption, and it produced an ash cloud that was more than 42 miles tall. So 42 miles of volcanic ash going up into the atmosphere, and it had enough volcanic ash that it was able to cross the entire North Atlantic and be deposited in these Scandinavian countries. So we can still look for the signature of the ash cloud 1856 when we take soil cores in places like Norway. So this is an example of a felsic eruption. And when we look at that Tephra Chronology record, what we find is that 80% of the eruptions have taken place in the eastern volcanic zone. 80% of all of the eruptions on the island of Iceland have taken place in the eastern volcanic zone, and 78% of those are going to be explosive. So it's a very intense place, that eastern volcanic zone. If you're lucky enough to talk to an Icelander who's 100 years old, they are going to be able to tell you about 25 different volcanic events that they have lived to. So if an Icelander is 100 years old, they have lived through 25 different volcanic episodes. So it's a testament to how active this island actually is. Next, I want to talk to you about some of my very favorite volcanoes on the island of Iceland. But before I do, what you need to recognize is that volcanoes in Iceland are given female names. And they're given female names for obvious reasons. They're beautiful, they're complex, and they have the ability to change the world around them. Thank you. My husband would argue that they're also dramatic and sometimes explosive. That's funny. I don't care who you are. So the first volcano I want to introduce to you is called Hekla. Hekla is, in Icelandic, translates to the queen. And in addition to Hekla just being a beautiful, beautiful volcano, I love going to visit her because and each of these are in the eastern volcanic zone, but to get to Hekla, it's a jaunt off of the main road. So people who are going to visit Hekla usually go there with some type of intention beyond tourism. So I've gotten to meet a lot of geologists and volcanologists and intense hikers by going to visit Hekla, so kind of sharing the same passions that I do. Hekla was quite a nuisance to those Vikings that established themselves in 874 CE. So when we look at the Tephra Chronology record, what we find is that Hekla erupted 18 times. And I can just imagine these Vikings getting their farmstead all organized, and then Hekla erupts, and now they got to go, and they got to dig out that volcanic ash, and they get it situated, and then Hekla erupts again. So quite a nuisance. But Hekla has also been really active in modern time as well. So Hekla erupted in 1970, 1980, 1990, 2000, and it's been dormant for the past 21 years. Hekla's gone through a dormancy phase for the past 21 years, and that's a big question mark for volcanologists. But the news just in is that yesterday there was a magnitude 5.2 earthquake that just happened at Hekla. So she might be stirring up. When we talk about the recurrence interval of Hekla, we said that she had a recurrence interval of every 10 years. That's also referred to as the repose of a volcano. So she did have a repose of every 10 years. And if you're living in the flank of a volcano, like you see this little cute farmhouse down here in the left-hand corner of your stream, you really want the repose of the volcano to be more frequent. Because remember, this is in the eastern volcanic zone, so you don't want that felsic magma stored and trapping gases. You really are more comfortable if the volcano releases its magnetism more often than not. Our next volcano is called Katla. And Katla was also a nuisance to the Vikings, erupting more than 20 times. But Katla is a much older volcano. So Katla originates about 10,000 BCE. And when we look at the Tephra Chronology record, we see that she's had more than 300 subglacial eruptions. So Katla is intensely glaciated, and over the course of her geologic history has had some pretty significant eruptions. The last significant eruption of Katla was in 1918. Oh, can you do the math? Pop quiz, 1918. So Katla has been dormant for 103 years. Oh, I'm going to leave that as a cliffhanger. Okay, that's your cliffhanger. Okay, approximately 30 miles to the east is this volcano, and you might be familiar with her. Everybody. Everybody, no? Okay, me either. I'm going to call her Aya. So when Aya erupted, you might be familiar because she erupted on March 10th, 2010. And the ash cloud that Aya produced was about 13 miles tall. So you get a 13-mile tall ash cloud that produced ash over the course of 3 days. And the ash was blowing in the direction of Europe. So it canceled approximately 100,000 flights. It affected about 10 million passengers and cost approximately $50 billion in gross domestic product. But what we said is that Aya is 30 miles to the east of Katla. And although each of these volcanoes have a central magma chamber, what's interesting is that they're also connected subsurface underground by a lateral magma chamber. So when we look at the Tephra Chronology record, what we find is that when Aya erupts, Katla erupts. And when Katla erupts, Aya erupts, because you're imagining like a bathtub effect of this magma coming from one of the volcanoes back to the other. So when you talk to any geologist or volcanologist about volcanoes to watch on the island of Iceland, the look always goes to Katla, because Katla has been dormant since 1918. So we're talking some pretty significant stored energy in this felsic, explosive volcano. It's estimated that when Katla goes off, it could produce an eruption the size of Askja 1856. So remember, Askja 1856 produced an ash cloud of 42 miles high, which was nothing compared to Aya, that was 13 miles high. So it's predicted that when Katla erupts, it might have the energy of 3 times that of an atomic bomb. So if you're interested in going to Europe, I'd recommend taking a boat instead of trying to get on a plane, because it's going to be a while. It's going to be a while. So we will look for Katla and her next eruption. Another volcano that doesn't get as much attention is the volcano called Surtsey. So Surtsey was number 13 on the volcanic diagram that I showed you earlier. And Surtsey is a volcanic island that's 20 miles off the mainland of Iceland. And what's great about the island of Surtsey is that it contributed such geological knowledge to our science, because when she first erupted in 1963, Icelandic geologists fled to watch the development for the very first time of a volcano emerging out of the ocean. The development of this island occurred over the course of 3 years, from 1963 to 1966, and those geologists took notes every single day and reported that there were 3.5 main phases of eruption to produce this now dormant volcanic island. It's even given a name as a Surtsean-style eruption, and so we look to the development of this island as an image of predictions of what can happen in other places in the world. Surtsey Island is considered a UNESCO World Heritage Site, but we're not invited to go visit her. So only Icelandic geologists are invited, and some evolutionary biologists are really interested in studying Surtsey Island because they've looked at the complete succession of life on this island since 1963. Unfortunate to us geologists is the signature of what Surtsey Island is will probably be erased in the next 20 years. So it's being erased and torn apart by the waves of the Atlantic Ocean. So we talked about tectonics, and we talked about volcanics, and that leaves us with glaciers. And this is one of my very favorite pictures that Joey Joey took on one of our hikes. This is Skatafell National Park. It's in the south of Iceland in the eastern volcanic zone. And when we talk about the major ice sheet that is remaining on Iceland, we refer to that as Vatnajökull. And at modern day, Vatnajökull ice sheet covers approximately 5,000 square miles of the island, or covers approximately 14% of the island. But the history of the Vatnajökull ice sheet goes back about 2.7 million years when we start to see her initial expanse. And by the time we get to 26,000 years ago, which is also called the last glacial maximum, the ice sheet on Iceland completely encompasses the island. 26,000 years ago is called the last glacial maximum, and it was a time when temperature was about 12 degrees colder than what it is today. So since then, the ice sheet has waxed and waned, and what we see now is that the melting of the ice sheet is expedited by greenhouse warming, leaving only about 14% to cover the island. When we talk about glaciers, what I want you to recognize is that these are systems that have a whole lot of energy, and it has a whole lot of erosive energy, and that they're not static, they're constantly moving. So when we consider an ice sheet, what you need to understand is that it's moving from high elevation to low elevation, or high gradient to low gradient, or high slope to low slope. And so as it's moving down, down, down gradient, it is tearing up the bedrock that is underneath it. And as it's tearing up that bedrock that's underneath it, it's entraining it into the ice, and it forms something that we call an outlet glacier. And that's what you're seeing here. So this is an example of an outlet glacier, where the main ice sheet is up here to the left, and here in this case the Atlantic Ocean is to the right. What we say in geology is the present is the key to the past, and the past is the key to the present. So even if and when this outlet glacier completely melts, we'll still have evidence of where the glacier was. When we look at this picture, what we can see are geologic features that are called lateral moraines. So you see these beautiful parallel bands along the U-shaped valley that is beginning to carve. And so those deposits will remain in place after the glacial ice completely melts. So it gives us a clue as to the glacial history that we see on the island. There's also something that's called a terminal moraine at the snout of where the glacier has pushed the sediment. The other thing is I want you to recognize is, again, how erosive and dynamic these systems are. When I took my first trip to Iceland in 2006, despite reading and studying glaciers through my entire undergraduate, master's, and PhD career, I really thought that glaciers were going to be pristine. Like, I thought they were going to be much more clean. But again, it's eroding and carrying sediment with it. And also, I want to remind you that there's 33 active volcanoes on the island of Iceland. So all that volcanic ash also gets incorporated into the ice sheet. And so you're seeing evidence of that sediment that's being eroded and probably volcanic ash. So we're flying up the toe of the glacier, and we're moving up towards the top of the ice sheet over here to the right. So you're seeing cracks and crevices, and the majesty of these can truly only be appreciated when you're standing at the base of them. But it gives you a picture of what that might look like. So the other thing you need to know about Vatnajökull, the ice sheet, is that it hides 4 volcanoes. So even if you fly over the top of Vatnajökull and you're looking down, you cannot see the peaks of these volcanoes because they're buried in approximately 3,000 feet of ice. So your question might be, Dr. Joe, what happens when you have a volcanic eruption underneath 3,000 feet of ice? And that is a catastrophic event, and we call these a Phreatic eruption. So you're imagining these volcanoes with their felsic magma chamber. So right, you're already in trouble, and that felsic magma slowly working up the throat of that volcano, already trapping gases, and now steam is being trapped underneath the ice sheet as well. So when she decides to go, she's going to have a volcanic event that's even more intensified by the presence of that steam. And oftentimes, when you end up with a phreatic eruption, you get a lightning storm in addition, because that volcanic ash that has cations and anions, we said it was silica rich, when that goes up into the atmosphere, it creates a static charge. So it's pretty challenging for geologists to study these phreatic eruptions because of the danger. Of course, things like flights are going to be delayed as a result, and it can influence how and when people evacuate. So you end up with a phreatic eruption. In addition to these intense eruptions that occur underneath the ice sheet, the other thing that can happen is a... Everybody, yoku. That's easy, come on, humor me. A yoku. We can do that one, we can do that one. So a yoku is a Icelandic word for a flooding event. And how this works is you have your volcano that's underneath the ice sheet. The magma is causing the ice to melt. And the good news is that the Icelandic Meteorological Society has a really good understanding of the shape and size and volume of each of these 4 calderas that's underneath the ice sheet. So if you know the volume it can hold, because it's essentially acting as a basin, and you know the rate at which the water is melting, then you can make some predictions when you anticipate a flood to occur. And that's exactly what they did in 1996 and in a volcano underneath the ice sheet that's referred to as Grimsvot. So Grimsvot in 1996 had a flooding event, and the volume of water, the discharge of the water flowing off of Grimsvot was 180,000 cubic feet per second. So the velocity of water was 180,000 cubic feet per second. And going into the Atlantic Ocean. When we look at the discharge of like the Etowah River, that's about 10,000 cubic feet per second. So we get this massive flooding event, but the good news again is that the Icelandic Meteorological Society could predict it because they knew the shape of the caldera, they knew the rate at which the water was melting and filling the caldera, and so they were able to evacuate, and no lives were lost. But when you have a flood that's directed toward the North Atlantic moving at 180,000 cubic feet per second, and there's a bridge in the way, the bridge gets taken out. So this is an example of the tangle remains of the flooding event in 1996. Skatafell National Park is in the back. So this is in the eastern volcanic zone. It took approximately 3 months for the bridge to be rebuilt. And that's a pretty big deal because it's on the main road, the ring road, and so it's connecting the east with the west. So if you think that's bad, let's return to Katla, shall we? We shall. So Katla is one of those volcanoes that's hidden underneath the Vatnajökull ice sheet. To make matters worse, right? She hasn't erupted since 1918, and now she's trapped under 3,000 feet of glacial ice. So this is an example in blue of an outlet glacier that's overcoming the Katla volcano. We can see the location of Katla. And again, when we look at the Tephra Chronology record, another thing that we can identify is past flooding events. Katla, a nasty volcano, right? We said that there were more than 300 subglacial eruptions. She's about 10,000 years old. And when we look at even just the modern day flooding events, we can go back all the way to 1612. And on this diagram, each of these colors represents a different pathway for the water from the flooding event will go. But I want to call your attention to this yellow pathway, because that yellow pathway represents an event that occurred in 1755. And it's estimated that this mega flooding event that has its own name, it's called the Katla because it's such a significant event in the geologic record in the world, not just in Iceland. The discharge was 1 million cubic feet per second. What? 1 million cubic feet per second of water flooding off of the flanks of Katla and going into the Atlantic Ocean. That's equivalent to the discharge of the Amazon River. So it's unheard of. It is a catastrophic event. So again, if you're interested in studying volcanoes, Katla is the one to watch. But I don't want to leave you with death and destruction, because that's not my style. Instead, I want to leave you with something happy. And so what is more happy than the Blue Lagoon? So your sister might have went to the Blue Lagoon. Your friends have gone to the Blue Lagoon. Kim Kardashian and Kanye have gone to the Blue Lagoon. And you too can go to the Blue Lagoon and for $70 can soak all day in a geothermal wastewater pond. That's not so sexy, is it? It's all about the marketing. It's all about the marketing. So how this works is that the Blue Lagoon is about 2 hours south of the capital city of Reykjavik. And Reykjavik has about 200,000 people living in it. So the population of Iceland is about 300,000. There's 200,000 people living in the capital city. And one of the means of energy is going to be geothermal. But Blue Lagoon, which is on the Rainies Peninsula, has really, really hot subsurface temperatures, right? It's close to that magma plume. And so the water that's coming out of the ground is super hot. And it's too hot to be able to be transported. So what they have to do is you pull the water out of the ground and let it cool down. And so this is like a holding pond for the water that will be funneled to produce heat and electricity for the capital city of Reykjavik. Additionally, on the Rainies Peninsula, there's a whole lot of felsic material. So it has a really high silica content, SiO2. And so that silica, because it's corrosive and it clogs pipes, has to be pulled out of the water too before it can be transported for use in Reykjavik. So the milky blue color that you're seeing here is really the silica precipitate. And when we look at this picture here, you can even kind of see the silicate in white that has precipitated. So the silica gives it that milky blue color. And when you're there, these beautiful Icelandic women are going to come along with these vats of silica, and they're going to encourage you to put it on your face for pictures, and you're going to do it. And then you're going to go to the gift store, and it's going to be really expensive, but you're going to buy it because they sell it as the fountain of youth. And it's a total hoax, but you're going to buy it anyway with the hope that you've found the fountain of the youth as you visited this amazing place. Maybe that's why Kim K went there. I don't know. So the great thing about Iceland is that it is 100% sustainable on renewable energy. So it's using about 13% as geothermal capacity, and the remaining 87% is hydroelectricity. And as you move away from that capital city, the farmsteads have what we call like micro dams or micro turbines. So they're very small, they're very sustainable, they're nothing like the Hoover Dam. And the message is that the Icelandic community is very conscientious of their environment. They very much are in tune with their environment, and they very much appreciate their environment. So they are conservationists as a whole, and it's nice that their energy is completely sustainable and allows them to protect their natural environments. And anytime we talk about geothermal, we have to talk about a geyser, and so I don't want to leave you without an image of what those heated subsurface waters look like. So I'm going to end my talk here. You've been a wonderful audience. Throw money, not tomatoes. And I need to thank some very special people. First, I need to thank my wonderful husband, Joe Cook. Could you stand up? If it wasn't for him, I'd still be lost somewhere in Iceland, I'm pretty sure. Another fellow in the audience that I need to thank is my former dean, Bruce Kahn, who is here. And hopefully you came early and you saw all the fantastic things that I get to do in all my global travels and my research in water quality. And I would have never had any of those experiences without the guidance and support of Bruce Kahn. So he's been a fantastic mentor to me throughout my entire career at Berry College, and I really appreciate everything you've done for me. So thank you, Bruce. Also on the screen, you'll see some fantastic Berry College students. All of those figures and diagrams that you saw and you see in the book, those were created by an undergraduate, and he killed it. His name is Nathan Minnan. I think he's on the YouTube Facebook channel with us here tonight. So we have to thank Nathan Minnan. Other students have helped contribute looking at the glossary and the references. Russell Madry took some of the pictures. You want to stand up, Russ? Took some pictures for the book. He went on my trip in 2017, as well his beautiful wife. So he was starting to learn photography and took advantage of that on the trip, and some of those pictures ended up in the book. Again, I need to thank Berry College Department of Math and Science for sponsoring that fantastic reception that we were able to have, and for purchasing the books for the raffle, and of course my publisher. And this is my news just in. I just found out this week that the book is the top seller for 2021 through the American Geophysical Union and Wiley. So it's kind of odd to think about, because I never thought that people were going to actually read it. I mean, I was just kind of doing it for fun. And it made it as a finalist for the Association of American Publishers Professional and Scholarly Excellent Award in Earth Sciences. So I am going to stop here. If you would love to go to Iceland with me, I would love to take you. I think you have that information. And I'm happy to answer some questions, comments, or short stories.
Okay, we have time for about 2 questions before we have to wind up. So I'm going to see this lady right over here has a question. So let me bring the mic since we're being recorded.
Can you speak to the similarity of the geologic features, particularly the columnar ones, as they relate to Yellowstone National Park?
Oh, very similar. Yeah, very similar process. That's interesting that you connected that. Yellowstone was once glaciated, and so you get the same type of formation, just in a different location, but again, related to a magma plume and hotspot. Yep. Cool.
Another question for Dr. Jovanelly. Yep, we got one right there. Wait, bring the mic.
Oh, I'm sorry. Can you speak to why there's rhyolitic magma and mafic magma all at the same chamber?
Felsic and mafic magma have different cooling temperatures. So mafic magma cools, solidifies, crystallizes at a much hotter temperature than your felsic magma. So your felsic magma is going to be closer to the surface as it crystallizes, and your mafic magma is going to be much deeper. In some cases, like that picture I showed you, you can get a volcanic eruption that has a lower magma chamber with mafic magma and a shallow chamber with felsic components, and you get both of those eruptions happening at the same time. So you might be familiar with the igneous rock that's called diorite. And so diorite has 50% silica and 50% irons and magnesiums, et cetera. And so it's an example of when you have these 2 magma chambers that are kind of working together. It's called Bowen's reaction series. It's an igneous process that determines the cooling temperatures of magmas with either mafic or felsic properties. Good question.
All right, well, join me in thanking again our speaker tonight.
Thank you. Thank you.
Remind you that the museum is open till 9 and the observatory is open till 10. Thank you so much for being here tonight.